Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward.
Welcome to Happy Path Programming. Oh man, it's a beautiful day in
It
Crestview,
is.
Colorado.
It's very nice.
It's just
early
springtime.
spring.
Yeah, delightful.
Yeah.
Well, today we have with us Jennifer Reif. And Jennifer, welcome to Happy Path Programming. I met you at DevNexus just like a month ago, and you have a podcast called the Break Time Tech Talks. Did I get that right?
Yeah.
And it's delightful. I've really enjoyed it. It's like these bite-sized nuggets of things. But welcome, and just introduce yourself and tell us who you are.
My name's Jennifer Reif. I've worked for
Your last
Neo4j,
name wrong.
which is a graph database company for the last 7 years now,
Wow.
and I've just really enjoyed what I do. I'm a developer advocate there. I focus mostly on the Java technology and ecosystem space, so anything having to do with Java tools and architectures and things that are going on in the Java space. Of course, where those collide with databases and graph databases specifically, I tend to focus on. And I really just like learning about technology and sharing what I've learned. So that's kind of how the tech blog came about. I write tech blogs, build projects, and then write blogs about what I've learned. And then now I've recently, I guess the middle of last year, started up a tech podcast as well. Again, just kind of a different format and focusing on bite-sized pieces that I learned kind of along the way, whether that's, project-related things or interesting content that I'm reading or tips that I'm picking up. So just a little bit of everything.
That's awesome. It's great that you have the opportunity to learn and then help others learn as well. So
Yeah, we like that.
we like that.
We do that.
So
I enjoy it too.
Yeah.
What have you been learning recently? What's the most recent explorations and learnings?
Yeah, so there's a lot of things going on. I feel like spring and fall are kind of the busy times for developer advocates. That's when a lot of events are going on. And so that's when I tend to build a lot of things all at once. And mostly for conferences and demos and applications and things around that. But I started working on recently for some conference presentations, looking at GraphRag and then diving into a little bit how vector databases are different from graph databases. And of course, how that relates to RAG and the retrieval augmented generation in the generative AI space. And just kind of digging
just a little bit of a intro to RAG.
Yeah. So generative AI is kind of where you have a large language model, as we've been using with ChatGPT and other types of interactions with these models. And generative AI is where it generates new content that's similar to whatever you've provided as input. Now, of course, we can do this through chat, but sometimes you get some really odd answers, or it doesn't have enough context to give you a good answer. And especially when you're looking at business applications or internal data to companies, the large language model is not going to be trained or have access to that data. And so as a way to improve the model's answers and to give it access to some of these things for people to ask questions about that specific data, you can do something called retrieval augmented generation, which is kind of where you augment the LLM's generative capabilities by kind of plugging it into a data source of some kind. So it's going to retrieve data from an external data source. That's the retrieval piece of RAG. And then it's going to augment the data that the LLM is trained on. It's going to add to that. And then the piece that the LLM is really good at, which is generating an answer in response to that. So retrieval augmented generation. It sounds a lot fancier, but you break it down and it's exactly what it says it is.
So I've recently started using, I don't know if it's still experimental, but ChatGPT has a button that says deep research. And it tells you what it's doing. It's like, okay, I'm looking at this site, I'm reading that site. Is that retrieval augmented generation?
So it's pieces of it. What I think the deep research, and I haven't done a whole lot of digging on that aspect thing, but what it's doing a lot of is agentic workflows or agentic processing, which is where it kind of steps through a logical process of these are the steps that I need in order to complete this full task or have this end result. And so it breaks down the steps that it needs to take, and then it might potentially call multiple tools in order to grab those bits of information from lots of different things, from different APIs, from different data sources, from, other models or so on. And it aggregates that information at each step. And as it completes one step, it moves on to the next thing. And it basically assembles all those pieces to complete the task. So that's kind of where you get into the agentic. RAG is a piece usually of agentic systems, but agentic kind of breaks out and does a whole lot more complex things.
It's kind of like a workflow around a bunch of different pieces.
Yeah.
So in RAG, we've got this LLM, and the only like API really to an LLM is I'm going to give you a prompt, and it's going to then respond with text or images or whatever
Right.
modal you want.
Exactly.
But so RAG is on the prompt side, where I am augmenting the thing that I'm giving to the LLM so that it can then give me back something that hopefully is better, more suited to what I need, has the data that it needs, whatever. Is
Right.
that the right framing for RAG essentially?
Yeah.
It's just like adding to the prompt some additional stuff.
Yes.
It's really what we wanted it to do all along. Is go out, find the information, give it to us. Yeah.
So the LLM can't actually reach out. So you have to have the thing around the LLM that's actually going to go do like the reading of some web page or getting some data from an external data store.
And at some point, we won't even talk about this because it'll just be what it does.
Right. Yeah, that's where you need right now the generative AI application layer in order to kind of handle all those talking back and forth between all the different pieces and assembling the bits of information. And I mean, technically, you can go out to ChatGPT. You can provide it a whole lot of background context, like, okay, here's an email I got taking this type of approach. Please respond to this person and tell them this and this. And I mean, that's kind of a form of RAG. You're providing additional context to the LLM in its prompt and sending that information back. It's just now, instead of having to assemble those pieces yourself and put them into the prompt, you're calling a database and letting it pull the relevant results and put those into the prompt and send that to the LLM kind of automatically, I guess.
Yeah.
Like you say, oh, here's my GitHub repo. Tell me what's going on with how I can do it better or whatever. You point it to that. Okay. And that's RAG.
Yeah.
It essentially is. Yeah. And I think there's like layers of this, right? It's like in the most basic form, RAG could just be, I'm going to add a system prompt. In some ways, like a system prompt is RAG. It's like augmenting the thing that I'm sending to the LLM and adding some information to it. Yep. Then there's the vector stuff and graph stuff, which we'll get into, and then there's the tools and MCP, which we talked about on our most recent podcast episode. And so all of this is just like giving more information to that call to the LLM so that it can hopefully give me back what I want.
Right.
Okay. Cool.
So that's kind of the basics, I think, of RAG and what's happening there. Let's talk about the different approaches. So in your realm of recent learnings and teachings, it's been on the graph and vector side of things. Give us an overview on those.
Yeah. So initially, when I started out, when AI really hit hard, I guess the end of 2022, early 23, vector databases were like the thing, the go-to storage piece for retrieval augmented generation. And I never really dug deep into how a vector database structures things or is organized. I'd really just kind of focused on how does graph fit into generative AI. And so this year I wanted to take a look at, okay, how are vector databases different? Why are they so hugely popular? And why is one better than the other maybe? And so I started digging into that a little bit. And I had been told previously that, it's so easy to get up and running with vector databases. You just toss something at it and it just kind of knows what to do. And it's not quite that simple, of course. Yeah. So I had a few hurdles getting data into Pinecone. I played with a couple of different vector databases, but I kind of Pinecone was kind of the go-to
out there now, right?
Yes.
lots of different options. The one I've used is PG Vector, which
Okay.
is built on Postgres.
Yep.
Um,
Can we back up a
oh yeah,
little
why do we need
and
a vector
say,
database?
well, no,
Or even
okay,
further?
let's start with the only experience I've had is with SQL databases, and I can't say I know how they work, but I have a sense of SQL. I've never successfully done an inner join or whatever. I've, all those things. So what's the matter with that, and what are the other options? I'm interested in the spectrum of things before we dive too deeply into it. So can you tell me
Yeah,
that?
and that's a great question, and kind of where I kind of led my learning path for getting into this as well, because I was trained and initially worked on relational databases. Before I came to Neo4j, I had never heard of a graph database before, had no idea what it was, and then just started learning about it and realizing, oh, they structure and organize their data differently. This has some really cool applications and use cases. And what you end up finding with all these different databases is they the challenges in one database, another database will often solve, because they've run up against use cases with one type of database that it just doesn't fit really well, or you have to jam the data into like really odd manipulations in order to get it to work. And then maybe performance is not as great or something like that. So,
So we've
like,
got in the kind of general space,
yeah,
we need to store data. We need to access that data. And most developers are familiar with doing this in relational databases, maybe NoSQL databases, like document
right.
databases, like
Yep.
Mongo. But then there are many other different ways that you may want to store and access data. And
Right.
so vector and graph being two of the many other options that are out there. And it
Yeah.
just so happens like vector and graph are a good fit for RAG. So we'll tie this all together to that. But
Yes.
yeah, I think we still need the overview of different data representations and
Yes.
why we would need those.
Yeah,
So
and I don't even know what a NoSQL document database is. So
I'm happy to discuss that because again, all this stuff was new to me as well, and it's just I'm adding bits of information as I go along to try to try to learn as I go too. So, relational databases are organized around tables and rows and columns. So you'll have a general table structure. You can think of like a spreadsheet or matrix or however you want to look at it, and it has a row which is a unique data piece, if you will, or
yeah,
organizing element.
it's like a
And each
spreadsheet,
individual
right?
row is
Like
going to represent a unique entity, if you will. And you organize those entities into tables, general categories, things like people or cars or businesses or documents or software projects, whatever it is. And then the way that you connect those data, so for instance, we might want to see what people are working on a software project, is that you write a SQL query to say, okay, I have a software project. So I'll go to the software project table, and then I need to do a join to the people table to find all the references of this software project and the people rows they're connected to. And so the more intricate the connections you have, like for instance, you might want to see, okay, which people are working on a project, which other people are working on similar projects in these departments. The more tables you have to join, the more complex those queries get. And typically, the larger your tables get, the higher index, the higher load that is to do all of those joins across because you're writing those joins at query time. They're not stored within the table structures at all. You're doing those lookups to the foreign keys, if you will, in each of those tables, which means you're having to do a full table scan and link across those tables. So anywhere where you have a ton of relationships and you're doing a lot of very complex, intricate queries on the relationships, that's where your typical relational databases, you'll start to see some performance degradation, is with those queries. So where NoSQL kind of came into play as kind of the next big wave. And that's where things like MongoDB and other, I guess you have a few different options there. You have like key value storage, you have document databases and so on. But document databases really kind of took the world by storm because they would embed some of those relationships within the document itself. So document just kind of being generally, I think of it like an object that you're storing, and you can nest some of those relationships within the original object. So for
so
instance, you might
in
have a software project document, and you could store the people's identifiers listed on that project document. So every time you pulled the project, you'd have the full list of people who were working on that.
So instead of having to do these table joins to get to the structures that you need, you just like have a document that has all that stuff just embedded in it.
And
Right.
so would you say that like the initial relational database model was emerged because, oh, well, this just seems to make sense as a way to store data because we're used to spreadsheets or whatever. And then later we discovered, it gets complicated to put the data together and the efficiency problems. Is this maybe how it evolved?
I think go ahead, Jennifer.
Yeah, my general thought process is that it wasn't necessarily that thought out. So, I mean, if you think about the way we used to store data, you had files in a filing cabinet. You go to the doctor's office and you have a paper file that somebody has filled out. You didn't really analyze relationships. You didn't look at, okay, this other doctor's office has this person's file and they've had these medicines for this type of disease or illness they had. Nobody talked to one another. It was siloed. So a table structure made perfect sense for that. But it's when this started growing and growing and growing, and then we started looking at, what are the connections between all these different pieces of data? And you started incorporating that. And as the complexity came up, then we started finding these no longer edge cases anymore, where you're doing a lot of those joins and it gets resource intensive.
And so, yeah, I think to your point, like relational databases became a thing probably because, organically it just was the path of least resistance to how we stored data. But then we reached the point where that model didn't work for everything.
Mm-hmm.
Yeah.
And so then we started to see the emergence of other alternative ways to store and access data.
Right.
And so,
And so what does a
graph,
NoSQL database do or mean?
Yeah, NoSQL is a very general, broad category, just meaning non-relational, generally. No
so we should really call it non-relational. SQL is very specific.
Yeah, NoSQL. They just wanted to get away from SQL databases.
Okay.
And so that is a general category that literally encompasses everything except relational databases. That kind of includes graph, it includes key value stores, it includes columnar scores, it includes document databases, and all kinds of other things.
Yeah. So with that background, should we go into vector or graph first?
Well, my trajectory has kind of taken me towards graph first. Okay. But I mean, I'm happy to talk anything.
Well,
but...
I mean, the way your trajectory sounds like the one you know best. So
okay,
let's hear that.
Yeah. So I knew relational. I kind of knew what document databases and Mongo looked like and the challenges they were trying to overcome from the relational world. And then I got introduced to graph databases. And what I realized through learning graph databases is a lot of the frustrations that I would just beat my head against a wall trying to write the SQL query to do in some of the other work I was doing with relational, graph kind of pulled those complexities apart. They have other challenges, to be sure, but the frustrations that I was seeing in the relational world, I did not see in the graph. And the reason for that is that the way a graph stores data is through nodes and relationships. So it breaks those each individual entities into nodes and stores them separately. And then you connect them via relationship. So it physically stores the connection between entities in the database itself. So a little bit more on the write side, much faster on the read side when you have a lot of like joins, if you will. So for instance, a person works on a software project who is within a department, who might have another colleague working on similar projects and so on. You can connect all those individual pieces via relationships. And it also makes it much faster when you have to refactor something, because no longer are you touching the entire table to update and change which project somebody is working on. You're just touching that individual person and the existing projects they might be connected to. So it makes refactoring and updating, maintaining data much easier and much simpler. I remember the days when I would have to touch a table and add a field or update something. You'd have to completely take something down, nobody could run stuff against that table until you were completely done refactoring it. You don't really have that in the graph. As long as those queries are not touching those specific nodes and relationships, you can refactor without touching and messing with anybody else's workloads.
And so it's a totally different model for how the data is stored, but then
Yep.
also how it's queried, because maybe
Yes.
you could simulate SQL over this, but the kind of native query language to a graph is a graph query language. Is that
Right?
So
Yeah. So go ahead.
why would is there any reason with the advent of graph databases, is there any reason that someone would still want to use a relational database?
Oh
Oh,
yeah.
there are. Okay.
Yeah. I mean, they're not used exclusively. There's not, one that's better than the other. It really kind of depends on your use case. If you're, for instance, just maintaining a list of people in your company and their job roles and their, salaries and contact information, and you're not doing a whole lot of joins, you just want to see who are the people in my company, then you wouldn't really need a graph database. You don't have a ton of connections. You're not doing a lot of really complex, like 6-7 hop relationship queries. Even if you're just doing a join or two, you're probably not going to see a huge difference in graph versus relational because it's not deep and complex enough. Where you start getting really hairy, though, is when you're doing multiple hops across multiple tables, a lot of subqueries and like filterings within certain patterns and so on. That's where your relational, you're going to see that performance degradation kind of slide pretty quickly. And that's where graph picks up and handles those multi-hop connections a lot better.
so? The more foreign keys you have in a relational structure, the more value you would see in going to a graph database.
Yep, absolutely.
Does a graph database distribute better?
It can. So here's the complexity because you're storing all those relationships on disk. It's hard to figure out how you break those structures apart onto separate machines or, wherever, right? So it is harder to shard or to distribute those systems. You try to keep the graph as close together as you possibly can because that just means it's not going to, when it has to hop across multiple computers and or whatever it is, to connect those bits of the graph, that gets complex to retain all those high quality data and good data integrity.
I guess the thing about your analysis of relational databases is you're saying, oh, if that's all you ever need, but an architect is going to look at this and go, I'm not sure what I'm going to need. And so it seems like maybe the safer bet might be a graph database or one of these newer database systems.
It could be. Again, it kind of depends on which challenges you want to face. If you have somebody coming in that knows relational and is like, well, here are the questions we're trying to answer. There's a couple of joins here and there, but we're not doing anything super complex. Then why not stick with what you know? Why not stick with, hey, we have people already trained and ready to go on a relational database. We're not doing anything intricately complex, or we don't need real time responses on some of these queries. They're ad hoc queries. They run overnight. It's no big deal. Then I wouldn't recommend changing that or altering something or learning something totally new just for the sake of it. However, if you do need those benefits and they're a major requirement for your business success or for the responsive nature of the application, then it is worth looking into having the right tool for the job.
Is there shining use cases of graph where it's like, oh, that's just like the perfect place to use graph? I think Facebook does a lot of graph stuff.
Yep.
So maybe like social feeds and all that is very graph oriented. I don't know. What are the places where it's like, oh yeah, obviously graph.
Yeah, social network was kind of the one that took the world by storm, I guess, as the first major graph use case, I guess, if you want to look at it. And so just, maintaining people's connections at any, one particular time in real time as people connected and sent messages and posts and comments and things like that. Tracking that is a little bit easier because it is so complex in a graph database. Other good ones, though, are things like fraud detection. So understanding how people and their identifiers and their financial transactions and accounts and loans and all different kinds of things all come together to create a unique financial aspect of a user. And then, of course, people try to take advantage of that by either stealing personal identifying information or creating loans in their name that aren't accurate. And so you can start to see this information pop up because you have all these relationships naturally in a graph. Another good one is like network and IT device management and asset management inside companies. So understanding what are my assets that I'm trying to maintain? Can I predict when they might need replaced? Or hey, we have one that's old and having issues. Should we replace that? What's it going to impact all down the line when we disconnect this thing? So there's those. I'm trying to think of other major ones that I'm drawing blanks, but there's tons. I always find there's new and interesting use cases that people apply graph to, and it's like, oh, I never even thought to use graph for that, but that is so cool that you're doing that. Biological and life science systems, health data management, and like patient connections and patient journeys. People are doing a lot with that. Recommendation systems for products and services that people might be interested in based on their past history and similar users to them, and so on.
Well, I want to ask two questions. One is
Sure.
just what's the ease of use? Because I think at some point you said, oh, people just say, oh, throw the data at it and it organizes itself or something like that. And the other is there a simple toy local graph database one would experiment with?
So there's a couple of things there. On the first side of things, just throwing data at it, I found never works for a database. For any type of database. Yeah. And that's kind of been my experience, with the vector stuff as well. But the biggest piece I think that is different for people when they look at graph databases is there's a little bit more upfront modeling work that has to be done because it is such a shift from relational world or even document world, where typically you will organize a schema, and that schema is very restrictive in what you can put into the data that you can import into that structure. And it has to fit that structure or it doesn't get imported. Graph databases typically are what's called schema optional, schema less, schema free, where you define that structure up front as kind of like a data governance aspect. And then you import that data to match that structure. But it doesn't necessarily, unless you set up certain guardrails, it doesn't necessarily restrict you from importing data in new and different formats. Again, that's where that kind of refactoring and moving and the agility of the schema comes into play in graphs. So that's, I think, the biggest thing is just formatting the data and organizing it into some type of data model that's going to be helpful and useful for your use case.
And so the developer in simple forms is going to do this. They're going to write their data objects in Python, and then they're going to use a graph API to then store the data and query the data and that sort of thing. So it's very similar in some ways to the relational world in that I have my data model in my code or my schemas essentially, and then I can use an API to the graph database to then do the storage and retrieval.
Yeah. The biggest difference is I see there's just a little bit more thought process that goes into the relationship piece of that and how you want to connect your entities. So you could take the exact same software project and people assigned to those, and 5 different people will model it completely 5 different ways. Where there's less of that, I feel like in the relational world, typically you'll organize the data in certain ways because you have the cardinality rules and so on in the foreign key structures. Yeah. It's a little bit more flexible in graph, which I think kind of confuses people sometimes.
Yeah. And to Bruce's other question on how do I actually use this?
Yeah.
There are many graph databases out there. Yeah. You're probably most familiar with Neo4j, so maybe give us the rundown on Neo4j and how somebody would get started with it.
Yes. Yeah. I'm slightly biased to Neo4j, of course. But there's lots of different ways to run graph databases. Specifically talking from Neo4j's perspective, we have a downloadable application that you can run local instances of Neo4j. So that's called Neo4j Desktop. And you can spin up as many databases as you like, but it's all local. We also have a Docker container as well. You could spin up Neo4j locally or someplace else, using a Docker container.
And
And then we
I've done that
have,
through test containers with Neo4j. So there's a
oh,
test
nice.
container. So super easy to integrate that into your integration test, your local dev.
Yep.
Love the test containers and love that
Yes.
Neo4j has support for test containers.
Yeah. Yeah, we have a few different engineers that work really hard to maintain that, and I know they use test containers quite a bit as well. So it's a really good implementation there. And then we have a lot of our cloud options too. So we have a variety of Neo4j hosted tiers of database. So we have a free tier, and then of course a sliding scale of paid tiers, depending on the business needs there. And then of course we're available in all of the major cloud providers too. So Google, AWS, and Microsoft.
So the name sounds like it's for Java.
Yep, that's a good question and one we get a lot. Yeah, originally this project was spun up by our CEO. He was a developer and needed to solve a problem, and so he wrote a Java library called Neo4j. So Neo being new, and then 4J is for Java, and that was kind of the big thing everybody was doing, is adding that 4J onto the end of things. And so that's what he did for the Java library. Well, and of course it grew into a completely separate database that you could run, on a server, now in the cloud. And the name just kind of stuck and stayed. So it's written not technically fully in Java anymore. They've branched out into other things in the source code, but yeah, initially that's where it came from.
It's always a little sad to hear, because you described him as our CEO used to be a developer. It's like, this is
don't let him listen
why
to
we
this.
need AI to manage companies, so the CEOs
Can keep
have
writing
to
code.
can
Yeah.
do what they like. Yeah.
And so there's clients then for Neo4j, and I'm sure every language that you would want to use it for, even though it
Yes.
had those Java roots. And
Yes.
so no matter how people want to interact with Neo4j, and then there's GraphQL, and we don't have to
Yes.
go into GraphQL, but so let's connect the graph data.
Before we go on,
yes.
does this have I don't know, a type system? Like, I mean, is it type aware?
It falls back mostly on a lot of the Java data types match up really well with the Neo4j cipher types, is how we define it. So our cipher is our graph query language. It is GQL compliant. So the GQL graph query language standard that was released last year, cipher is compliant with that. That is totally separate from GraphQL, which that could be a whole other conversation. But Cypher is the way that we interact with the data inside Neo4j, kind of like you use SQL
Like
to
SQL,
interact
yeah.
with data in a relational database. And the Cypher type system is very similar to Java's type system, but not everything perfectly aligns. But we have all your major data types, like, text and links and I'm
Does
drawing a
it
complete
support?
blank.
I mean, like Java has a relatively new record um, mechanism. I mean,
I
you're
mean,
probably familiar with records.
it's a database, so
Okay.
it stores data on disk just like a relational database or anything else does, and you
Sure.
can absolutely map it to Java records or Java entities when you pull that data out of the database. But we don't store things as kind of Java objects, I guess.
Mm-hmm. Okay. So your types are basically the Java primitives, primitive types.
Yes. Yes,
Just
we've got a few complex types like points for geospatial and some of the date time types as well.
those are
But
predefined.
yeah,
Okay. All right. Well, that gives me an idea. Okay.
And then you map that back to your data structures on your
application side.
Right.
Yeah.
Sure.
Yeah.
And were you about to
Oh.
ask about vector?
No,
databases?
so let's go from graph to RAG,
Okay.
and then we can probably talk about vector as well.
Yeah.
So it does seem like in the LLM Gen AI space that graph databases have gained this new superpower and usefulness. Unravel that if
Yeah.
you maybe agree or disagree. That's fine.
So it's kind of funny. Neo4j didn't really plan to be a major piece. I mean, we all wanted a piece of the Gen AI hype for sure, and the Gen AI wave, but it kind of GraphRag kind of just fell into graph databases vendors' laps, right? People realize that, oh, a graph is super helpful when you're retrieving information from external sources and adding that to the LLM. The more context and relationships you can give to that input, the better your response is going to be. So, for instance, let's say we have, going back to the people and software projects, let's say that you want to ask the LLM something about, what are all the projects that I have um, in this space? And it would go out and look for those software projects and it would retrieve the similar results and send those back. But now I could hook that up to a graph database and say, okay, I have all these projects. Here are the departments they're in. Here are their budgets. Here are the people that are working on those. Retrieve all those related entities and send that to the LLM. And now all of a sudden, my response is going to be much more detailed and much more specific. Like, here are the projects you're working on. Here are the topic matters and the business problems they're trying to solve. Here are the departments that head those up. Here's kind of a few people that might be working on those for contacts. And now you get all of that information being added to the LLM and to provide that as a response.
Just throw it all back to the LLM and let the LLM, with all that context, then figure out what to give the user as a response. So,
right.
So it's about the special sauce of graph here with RAG is the context, which is relationships. And
Yep.
so now we can provide so much more contextual information in the graph kind of structured way to the
Yep.
LLM, which is the more information, the better.
So does it, it sounds like the graph database is quote unquote easier for the LLM to use. Is that possible?
It's easier for us to, as developers, to construct what's relevant to an input because we have all that extra context. The example that Neo4j initially used and that I like to revert back to is we dumped SEC Edgar filings into financial filings into Neo4j, and then pulled in some external data sources for like companies and people who owned stock in those companies and so on. And we dumped all that information in. And initially, when you would ask the LLM, what are the liabilities for those who produce lithium ion batteries? Like, what if something happens to the lithium ion battery industry? What's that going to impact? And it would retrieve, little bits of information. But then when you add that in the graph and you say, oh, now I have these companies that are focused in this general industry, and here are the stock pilings that add on to that and the people and other companies that might be impacted by those things. Now all of a sudden you get much more detail, much more relevance when you're looking at, okay, what's the impact to the lithium battery industry if this happens? And you get all these extra pieces and you can follow up and say, oh, we're actually going to impact this area of our organization we didn't realize. We need to reach out to these people and see what we can do to mitigate that risk and so on.
It's fascinating because the LLM, the model of it is relationships between things. And so it does make sense that if it then has data given to it in also relational form, that it's going to be able to
relationship form.
Yeah. Yes. No, sorry, not relational. Yeah.
That's a misnomer. Actually, relational database isn't actually super heavy on relationships, right?
Yeah. Oh, yeah. You're right. You have to put the relationships in.
But if you provide data in a graph structure to something that is modeled as a graph essentially, then it seems rational that this is going to give you better output.
Yeah, and really it's just helping guide the LLM into the general path of the correct probabilities to respond back. And the more information you can kind of guide it into pieces of its memory and knowledge, the better that answer is going to be. So if you can direct it, hey, when I talk about asset managers, I don't mean, people who own the companies or CEOs. I really am talking about people who own stock and actually own financial interest in the company. And you can kind of direct it into the right area of its knowledge. And then when it retrieves and sends information and generates the information back to you, it's much better quality because it's more what you're looking for.
Yeah.
What pops into my head is that a lot of people are getting away with things by hiding. It's like all the information's out there. It's just hard to get. Something like this is going to make that harder.
Yeah, and that's where things like fraud detection, it's super useful for doing that because it surfaces all of those connections that are much more hidden in a relational database structure. It surfaces those relationships in a graph and it makes them very much easier to see, I should say.
Mm.
Do you could you walk us through, okay, I've got an agent, it's talking to an LLM, and I want to hook that to a graph database. Like what's actually assembling the query and like what's that process look like?
There's a couple of different methods there. So you could use something like text to cipher, text to SQL, which are libraries that you ask a question to the LLM, and usually you try to define your data model to the LLM so that the LLM has, again, extra context reference, and then it tries to generate a cipher or SQL or whatever query based on the input and the general data structure that you have defined. We've had mixed results there. Some of them actually are really, really good, and then others are kind of like, that's not the greatest query. But an LLM will kind of do that and do that reasonably well. The other structure is kind of what I have done in the past, which is okay, I know I have these relevant entities that are coming back from a similarity search, which we could talk about separately. But what's relevant to this input, and it'll retrieve the items from the database that are most relevant. And then I write I guess, a user expert query or a
Mm,
developer expert query, technical expert query to go out to the database and say, here are the entities that I have. I want to retrieve these pieces of the graph that are related to that and then surface that information up. So there, again, it's kind of a two-pronged approach. Do you let the LLM figure out what's important and what's relevant based on it writing a query, or do you have someone who's an expert write that query to define based on this type of question? These are the extra things that I want to retrieve from the graph.
gotcha. Okay. So different approaches and probably different use cases where
Yeah.
each of those would make sense. So in the latter example, we see that a query comes in for something related to people. And so then we're like, oh, I've written the query, the graph query that knows how to get people and all the things related to people that the LM may also want to know about.
Yes.
And then I can make that query, feed the results, rag it into
Yep.
the prompt.
Yep. Yeah, and you can define like a series of one example I saw actually just this week is that somebody had defined a series of tools for a variety of different queries. Like, okay, here's my person query, here's my software project query, here's my this or that query. And then basically the agentic system would determine based on the input that I have, which query should I run, and then it runs that query and retrieves the results.
Yeah. Yeah. So let the LM figure out the workflow and
Right.
throw MCP in there because, yeah, everybody
Yes.
needs some MCP in their life. Okay, so you did mention similarity search, which I think
Yeah.
would be a good area to go into next. So give us
Yeah.
a rundown on that.
Yeah. So basically, this is kind of where the vector database space overlaps is in the similarity search. So previously, databases did what was called a keyword search or lexical search, as you might hear it now sometimes. And that's just basically where I have this, bit of text that I want to search for, this particular value I'm looking for in my data set. And sometimes you could do fuzzy searches or you could provide it, dictionaries of synonyms and so on that could look for as well. But that was somewhat limited into exactly how you defined it. So if you didn't have the direct specific synonym, it wouldn't find that one, right? But now what we're able to do is we needed to be able to search large corpuses of data that are semantically similar rather than just
Mm,
keyword or fuzzy search similar. And so this is where you had people create a vector representation, a numeric representation of data. And the way they do that is they pick out key specific features about a piece of data. Let's say, for instance, if we want to do that for a word, the example I always give is let's say we took the word king, and Google actually did this. They turned vector representations to words and all the things that we understand and the way we use king in language. So, ruler, wealth, leadership, lives in a castle. Those are all particular features. And then, based on those features, you can create a list of floats, an array of floats, numeric representation of that word. And then you can use it if you do the same thing for other words. You can start using it to compare how similar are these two concepts or how are these two words used in the English language or whatever language you happen to be looking at.
Huh.
But of course, as you do that for more and more data, we can now do that for all different kinds of data. We can create vector representations or embeddings, as they're often called, for images, for text, for videos, for documents, and so on. And we can create these numeric representations. So now we can compare lots of different types of data modalities, if you will, that we couldn't before. We couldn't take a piece of text and say, how is this similar to this video? Now we can, because we can create a numeric representation of the interesting features about that. But of course, the more data you have, the more challenging a search is across all that data. So now how do we optimize that? How do we make it easy? And that's where vector similarity search and where you have things like the K approximate nearest neighbors algorithm come into play, where it tries to select the closest similar results with a couple of different dimensions. The first is like a cosine similarity, so the angle of those vectors, how close they are together, or there's a Euclidean distance, which is kind of as the crow flies between these two vectors in space, how similar and how close are they in the multidimensional space. So you search and find the 10 nearest neighbors or 50 nearest neighbors or whatever it is, most similar to this numeric representation of this piece of data. And then you can surface those relevant results. And that's going to pull semantically similar things.
Huh. So this is a way to represent data in a method that then can be used in a similarity search. Is that
right?
I think I just said everything you said, but
yep. Yeah, the joke that I like to make is, people always teased previously about, oh, you can't compare those two things. That's apples and oranges. Now we can actually create a vector representation, numeric representation of an apple and an orange, and actually compare how the two things are similar, because we have a consolidated, unique representation, a comparable representation of all these different types of data now.
Yeah. And so, and I like your apples and oranges example, because the commonality between apples and oranges is that they're both fruit. And so the vector representation would allow us to identify the relationship between apples and oranges through
how
in a
similar are they?
mathematical way that we could search against.
Right. Yeah. Their skin is different. You eat them differently, but they're similar in size and color, and they're both fruits, right?
Yeah. Huh. Cool. So then we've got the vectors for our business data. Like, would we take our employee database and vectorize it, and so that then we could do similarity searches across an employee database or something like?
You can. It really depends on the use case you're going after. So for me specifically, like, I have a book recommendations data set, and I took user reviews that people had written about books, and I took the text and created an embedding of that, and then do a similarity search on, okay, I have themes that I really like in books that are very, very specific. Right now, you walk into a library and you're very limited on, well, I like science fiction, which is in the fiction section, half of the library, and it's within the science fiction genre. And then you're just left kind of picking and choosing, okay, which author do I want to try? I have to look at the back of the book to see if it's interesting or not. But what if I could pick something very, very specific? And let's say, okay, I'm looking for a fantasy book. I really care about dragons and magic. What are the books that have dragons and magic? That's a much narrower search set now, and more semantically similar. And now I get much more relevant results and things that I care about in that.
Nice. So that makes sense on the value of it. How does this then relate to LLMs and Gen AI? Why do we need it there, and how does it fit into RAG?
Yeah. So again, it's the way that I see it is that you can't just plug an LLM into any particular data source. It doesn't understand. It understands text, understands images, or whatever modality the LLM is trained to understand, right? But it doesn't necessarily understand data structures, relational databases, graph databases, whatever. And so a vector representation makes a consistent, easy, searchable way for us to retrieve what's semantically similar to the user's input, whatever they happen to be looking for, and then provide that data in a way, and you don't have to provide the LLM with the vector. You actually provide it the data that's coming back, but the vector representation just makes it easy to search semantically for what you're looking for. Okay. And then you provide those relevant bits of data, the actual rows, if you want, or the objects or whatever you're pulling, and you feed that to the LLM as text, and then it knows what to do with it.
So in your case, we have, let's say, an agent that is my library search agent or something, and natural language, you say what you said about you like dragons and want books that are like that. So then that would your agent would actually do the similarity search against your vector database,
Yeah.
and then provide the responses from that similarity search to the LLM. And
Yep.
then that doesn't necessarily mean that's what the LLM is going to give you. It's going to then augment that with, its information and its knowledge and the question that you asked it to give you the actual response. Am
Yeah.
I understanding
Vectors
that?
are really just a mechanism for us to search all different kinds of data that we couldn't previously search. If it wasn't stored in a database in a readable format somewhere, like for instance, all the PDFs and all the like lessons learned documentation that organizations might have, that data was not previously analyzable or accessible to any system. And now that we can create a vector representation, that data is all of a sudden useful and searchable.
Nice.
We could
And
search
then
image databases or video databases or whatever.
yeah. And then the process of creating the embeddings or the vectorization of this
Mhm.
data, are we using LLMs now to actually do that? Is that how that works?
Yeah. So you'll call an embedding model, which is a model that has been trained specifically to take data and create a numeric representation based on key features or important things within that data. And then it spits back out a vector representation of that. And you
And we
save that
need
to
to
your.
use an embedding model to do this that has a
Mhm.
lot of knowledge because it um, it needs to know lots of things to create the vector representation.
Yeah, what are the key features? What are the prominent things in this data that's being provided? And then generate a series of numbers based on the probabilities of all that, and spit that number back out.
And then the embedding database that I worked with recently was Cohere, and then you
Okay.
could use it either in a English only mode, which I assume is just like if it knows that it's only talking English, it's
Mm.
faster and smaller.
Yeah.
But then there was the multilingual model, which could understand probably many languages, so probably a
Yeah.
much more complex, larger model. But then there's other embedding models for images and videos and other modalities, right? So
Yeah.
that depends on kind of what we're creating a vector representation of, which kind of embedding model we'd want to use.
Right. Exactly.
So, and then different data storage databases that can store the actual vector representations once we've created the embedding from a model.
Yeah. Vector databases from the outset were really well designed for this because they were optimized to store the vector and then just a little bit of metadata alongside that. So, and then they were optimized to do those similarity searches and to handle those really well. So that's, I think, why initially you saw that explosion and the huge popularity of vector databases. But then, of course, every other database on the market was like, well, wait a minute, we can do this too. And so started tacking on vector functionality and capabilities and indexes onto their existing data structures in order to help support these as well. So that's why you'll see graph databases. A lot of the graph database vendors will now have support for vector indexes and vector storing the vectors. You have things like PG Vector is Postgres relational database that now adds capabilities and optimizations for storing vectors and searching them. And every other database on the market's doing the same.
And Neo4j does.
Yep.
Okay. So you're not really taking, like, if you're going, oh, maybe we need a vector database, you're not really taking a risk if you use a graph database. You can still use it as a vector database.
Correct. There's some that argue that jack of all trades, master of none. So the more different kind of features or functionalities you tack on, the weaker those are going to be. And that was one of the reasons why I started playing with vector databases, is really to see, okay, what strengths and weaknesses do they bring to the table, and is it better to go this route? And for just the use case that I've done so far, I haven't seen a huge difference. Vectors have the vector representation. They're meant to be quick and efficient about retrieving those. And then they pull just a little bit of metadata. So you're not going to be able to pull a whole lot of relationships with that. But again, is that vital to your use case or not? It really depends. And if you're retrieving a ton of vector similarity and doing a ton of vector similarity searches, maybe the vector database is the better way to go. But at least for the use case I've done so far, I haven't seen a whole lot of variation in the two. So it really just depends on your use case and maybe the load that you're putting it through.
And is there a scenario where it's a both and, where you want in your agent, your AI agent, to be able to do a similarity search, get that piece of data, then get me the relationships that I want related to that piece of data, and then feed all that back into the LLM together?
Yes, and I've seen people talk about this, and I don't know if anybody's actually doing this in production yet, but we've seen where people have explored. Okay, I'll store my vectors in a vector database. I'll query those, then go out to the graph and retrieve those. The benefits that I see there is, again, a vector database is optimized for storing and retrieving the vector. And then you could go out to the graph and not mess with storing these big, large arrays of numbers inside your graph to potentially take up storage space, especially if you have like really large graph, maybe. And then go out and just retrieve those related entities based on the IDs, from
Mm-hmm.
those vectors or something like that.
Yeah.
And I've seen people explore and do things like this. And again, picking the right tool for the job depends on your use case.
Yeah. Huh. Super fascinating. It feels like I don't know, a few years ago, maybe I don't know, maybe 4 years ago or so, no one was really talking about vector databases.
Mm-mm.
Graph was still interesting in a lot of ways, but it seems like the LLM Gen AI space has just exploded both of these concepts, vector
Yeah.
and graph, just because it's like, oh, we've got these new ways that we need to interact with and query data, and so that requires different representations of that data, different storage mechanisms. And so it's kind of a fun time to be in that space where it's like, okay, yeah, a relational database, probably not the best fit to work with a LLM that wants to be able to like join data, needs the context, that sort of thing. So
Yeah.
Are there new technologies on the horizon for databases? New, you know.
That's a really good question. You're starting to see like a lot of agentic things surface quite a bit, where you're having the LLM decide which tools to call and in what processing order. There's also a lot of talk about agentic memory, which is looking at the memory of the chat. And again, all those relationships, there's a lot of data connections there between the memory and all the pieces that are being called and the external resources that are being called in and pulled in for that. So I think there's some research and exploration being done on using graphs for chat or agentic memory, and kind of process flow. So looking at evaluations and how are people interacting with the systems. You can see all of that really well in a graph. So I know there's some things being done in that space. As far as what the future will hold in AI, I think that changes, on a daily basis in a lot of cases. So who knows where we'll be in, 6 weeks or 6 months, but it's definitely a fun and exciting time. So
I'm glad you pointed out the chat memory, because this is actually, I think, a place where graph is a really good fit. Because so chat memory is, I've got this sequence of conversational things that I've had with the LLM, but the in that conversational history, there's likely relationships to a ton of different things happening,
yeah,
and deeply nested relationships as well. So I called this tool, I got this piece of data back, I augmented it with this other piece of data from this other system, and so on and so forth. You're like building the relationships as you move through a chat or an agent history. And so
yeah.
graph becomes a really good way to model and then be able to query in the future that that whole database graph of interactions that happen.
And
Yeah, it's
I've
all
noticed that, like, the AI has been saying, "Oh, do you want me to do this for?" Because it's like, quote unquote, aware of, "Oh, I'm working on this project, and that's why I keep asking these questions." And so it's making suggestions about things I could do next based
yeah,
on that context that it's holding.
Yeah.
yeah.
And that
Yeah, and
context being well represented as a graph
Yeah.
is
and
important.
it's also a really good thing for like understanding the operational usefulness of your system and for auditability too, because now you can all of a sudden track where this thing's moving and how the system is operating and how users are interacting with it, and where are their successes and where are their failures, where is the system letting them down or not providing as much helpful information as it could, where is maybe the LLM getting stuck and caught in a loop somewhere that maybe it needs to be kind of pulled out of. Could you improve your information and your supporting documentation to help it kind of break out of those things? Can you help users get to their solutions faster instead of maybe 16 messages from the user? Could you get them there in 5, and so on? So being able to see and understand these processes and the interactions that users are having with systems, I think is super interesting to see in a graph structure.
Yeah.
So you're obviously very deep into this, and we are too. I mean, I started using AI as soon as it came out, I think, and but I've read some. I mean, okay, there's the usual panic articles which say, "Oh, programmers will never work again," but I have recently read a couple where the person was going, "Okay, well, this is, yeah, it's another tool like a compiler or whatever," um, and the argument that this person was making, I think he was a CEO of an organization or something, he was going, we can now solve more problems. To think that we have we've run out of problems and the AI will solve them all is kind of silly. And so his perception was that we will have a, in a, maybe might take a couple of years while the ship's around, but we will have a greater demand, which has always happened in the past
Yeah.
for programmers. They will be working at a higher level, they'll be more productive, etc. But there's
Yeah.
so many other problems to solve that we have
Yeah.
that just are not on our radar because they've been not economically feasible to solve, and so we
Yeah.
just go, oh, well, we don't solve that. It's not a problem because it's not economically feasible to solve. And now this is making it, and that's my perception, is that it's opening more possibilities than it's closing. But do you have opinions about that?
Yeah, my thoughts are that it's a way to delegate tasks to an AI, and to handle the things that maybe we could take more off our plates, and then allow us to, again, as you said, open up new possibilities and other things we could be doing. We're still, I think, a human is vital to have in the loop for these AI systems. You're going to need those cross checks and those verifications to make sure that the systems are still doing what they're supposed to be doing and are still providing the benefits. And you're going to need some interaction on a human level for that. I just listened to the other day, somebody was talking about, well, you have people now going in and doing fine tuning, and you need humans. You're hiring humans to help do that fine tuning. Like, okay, here's the input, here's the output. Let a human check and see if that's valid and see if that looks good. Yes or no. Provide that feedback back to the LLM and then train it on whether it was a good answer or a bad answer. And so again, you're changing the way we're working, our productivity levels and the tasks we're working on, but I don't see necessarily humans being cut out of the loop, at least not for a long while, right? I still think humans are very vital to that loop and necessary. It would be a sad, strange, crazy, unfortunate world to hand it over to the AI as it is. But I do see us maybe adapting and changing our workflows, but I still think like architecting the systems, designing, maybe higher level, like philosophical thinking is where we'll come in and do more of those spaces. And like you said, there's new problems that we haven't had a chance really to think about or solve. Now maybe that opens up brain space for us to be able to do that.
Sounds good to me.
I mean, I feel like I'm empowered and I can solve more problems. And there's a lot of problems that I didn't try and solve because it was just going to be a distraction, a rabbit hole to go down, and it wasn't really worth it. And
Yeah.
now I go, oh, I want this to happen. And at least I try and
Right.
see, can it solve it? And very often it can. And I go, oh, now my productivity is better.
Yeah,
And I
I'm
can
not
solve
sitting down spending hours writing unit tests, right, and coding unit tests. I'm
big.
saying, LLM, please generate some unit tests for me. And then I'm going through and making sure that the use cases are valid and that it's actually producing the outputs that I'm looking for it to produce. And then I move on and do something else.
Hmm. Yeah, I think he was saying that humans are going to be the guidance for the what it is. Our creative aspects are, oh, we see the problem that needs to be solved that the AI doesn't necessarily see, and
Right.
they'll get better at that and everything, but they will need guidance, and we'll be able to come up with yeah, I don't know. I'm not worried, but I've been through this
Yeah,
this whole
LLMs are
cycle.
not sentient at this point in time.
No,
They
no.
don't understand and comprehend, and I mean they solve limited problems, but they don't look at bigger pictures, and they don't look at kind of general problem spaces and try to figure out solutions to those in a humane and um, economical way, right?
Yeah, and I think we probably will get AGI at some point, and eventually it will be, well, the way I describe it to people who are panicking is that it's a science machine. It will give you better and better answers, but it doesn't. I think Feynman said this. What he said. I think he was talking about computers in general. He's going, computers can only give you answers. I'm interested in questions. And the humans will always be the ones asking the questions, even if it's just, can I do this better, or can you do this for me, or whatever. We'll be the ones that come up with those.
Yeah.
Instead of trying to cure cancer, we'll move on to other bigger, better
Right.
things possibly
Exactly.
after that's solved.
That's what we've always done.
Yeah.
Hopefully we've asked good questions and we've done it in a way that the AI could not replicate.
Fair. Yeah.
Thank you for all your answers and insights and teaching us all about this stuff. This was fascinating because it was a space that I needed to learn and wanted to, and now I'm excited to dig deeper. So yeah, really appreciate you sharing all that with us, Jennifer.
Thank you so much for having me. I was super excited about this, and I feel like it was a really great kind of back and forth conversation. Lots of good questions. So
that's what we like to do.
I learned a lot. So
yes.
Thank you.
Thank you.
Yeah.
Hey.